Hello and welcome to this manufacturing process technology part 2 module 41, and we are beginning a new section today on metal forming. As we all know, forming is one of the primary manufacturing processes which is able to give the overall shape and size to the material just like casting does, but here the basic principle is quite different. You basically operate in a range, particularly in hot working operations, where the temperature, operational temperature, is just below the solidus temperature, and then basically provide mechanical energy to the material to take it into its flow stress region so that it can flow and take various shapes, and that's how the overall forming strategy works out to be. So if we look at the basic categories or classifications of the broad term metal forming, really can be classified into two different domains. One is all the processes related to bulk deformation, where there is a deformation along the bulk of the material. Some processes may represent bulk deformation as rolling processes, forging processes, extrusion processes, drawing processes, so on and so forth. Then there are again different set of or a group of processes called sheet metal working processes, which again come into metal forming domain. For example, bending operations or deep or cup drawing or shearing processes, some associated processes like this. So they are classified into the sheet metal working process. So you have categorized the whole forming domain into either the bulk deformation processes or the sheet metal working kind of processes. If we looked at what are going to be the terminologies associated with metal forming, the first thing that comes to our mind is what we know as a bloom, billet and a slab. Okay, so these are some semi-finished products. In fact, from a casting or a steel industry, what is produced as an output is either an ingot or maybe a first breakdown of the ingot, which is known as a bloom. Here, for example, it shows a cross-sectional area of probably 6 inch into 6 inch or larger. So this is really how the raw metal comes out, as ingot or a breakdown of an ingot, which is a bloom. Also, if I were to further reduce the bloom into a billet through hot rolling process, you could typically have the areas in the range of again from 6 inches, which is about close to 150 millimeters, all the way to 1/4 of the value, so 40 into 40 mm sections. So these are categorized as billets. So these are again another finished product coming out of forming processes. Okay, so over and above what the casting does, you have to now give material as relevant material to the industry so that it can be commonly shaped or sized or can participate into assembly processes. Then you have another kind of semi-finished product called slab, which may generate again by hot rolling processes over the input from the casting industry, ingot. In fact, the term bloom here is really out of the very commonly used furnace, very primitive commonly used furnace called bloomer, and in fact it shows how the output of such a steel industry can be, or wherever there is steel processing, how the output would really shape into, which is handleable. It can be translated into various manufacturing processes, subsequent manufacturing processes, and so therefore these sections form very, very important in terms of the inputs to the other manufacturing processes. Okay, so a slab is typically one where the cross-sectional area is greater than 100 centimeters and you have a width of almost either greater or equal to twice the thickness. So at least that is how at least twice the thickness is what the width should be for material to be, or for a shape to be called a slab. So you can have these various products, bloom, billet and slab, out of forming processes as the first shaping which happens to the casting ingots. There are some other associated processes which are of importance. One is a plate. Okay, so this is a product with thickness of greater than 5 mm. There is a sheet, which is again a product classified by a thickness at least less than 5 mm but a width of over 600 mm. And then finally a strip, which is again a product of the metal forming process, which can have less than 5 mm thickness and almost less than 5 mm 600 mm width. Okay, so you can further categorize the finished products of milling processes as plates, sheets and strips. So you have the first end process, hot rolling applied to ingots from the casting, creating billets and blooms and slabs, and then you can also further reduce or downsize to plates, sheets and strips. So that's how the various steps can be thought of the steel industry to produce raw steel, which can be given for the various later on machining or assembly processes. Now having said that, the important term which is associated with all this is deformation. And as we all know, there is a very famous stress strain curve for any ductile material as represented here. It indicates a range which is actually where the stress and strain are proportional to each other, also known as the proportional limit or the elastic range, beyond which there is a some kind of maximum point up to which this sort of elastic behavior can be observed, beyond which there is something called a permanent set or a deformation. So here, for example, this is the yield point of the elastic limit up to which you can find out the deformations to be primarily elastic. As we all recall from basic solid mechanics knowledge, elastic deformations are entirely recoverable once the acting stress on it is removed, on the material is removed, and no part of the object under stress may have undergone any kind of permanent set or permanent deformation. But beyond this point B, there is obviously going to be a point where any further increase in the stress level would result in some kind of a permanent set, okay, or a permanent dislocations induced within the crystal structure, so that the overall size and shape changes. So this point B then is known as the yield point or the plastic limit, and deformation beyond this elastic limit, typically the curve from B to D region is also known as the plastic deformation or the plastic flow. Okay, and what essentially it means is that due to slip or due to grain fragmentation or even movement of atoms or lattice distortions, all these different phenomena, the metal kind of moves ahead and doesn't come back. So you cannot recover the stresses into the system once the system is in the plastic deformation range or plastic deformation region. So in a plastic region, the metal's behavior would be expressed by this famous flow curve equation, which is basically about the relationship of the true stress and strain. As we all may recall, again, the value of the true strain is actually provided by the integral of dh by h between two different thicknesses. Let's say there is a initial block of height h0, initial height of h0, and we are applying a compressive stress so that this goes to h1. So on application of a compressive stress, so basically the true strain in this case can be recorded as integral h0 to h1 dh by h. Okay, so you can actually represent this by ln h1 by h0, and basically can also be recorded as minus of ln h0 by h1, where h0 obviously is more than h1 in this case, the initial height, because it's a compressive stress system that we are applying. Initial height is more in comparison to the final height. So such a situation, the true strain can be defined by this logarithmic ratio between the initial and the final direction in the same axis as the axis of the stress. So the relationship here is between such true stress and true strain, and it's basically represented as sigma equal to k epsilon to the power n, where this n is basically again very commonly known as the strain hardening exponent, okay, and k is also known as the strength coefficient, typically expressed as megapascals, particularly in case of steels, etc., or other ductile materials. So we are really interested in looking at this end of the curve. We are interested in looking at this from B onwards all the way, to let's say the point D, fracture point, and here is where we have to lay down all the forming processes, and typically we will have to in a step by step manner arrive at certain criterion which are useful to estimate the kind of forces which would be needed for the material to flow into a range where yield can happen, or the ultimate yield strength can be caused, so that forming processes start happening or metal starts getting formed, okay. So there are certain useful rules or relationships which are important in context of metal forming. One of them is that for plastic deformation there is always a constant volume relationship, okay, which is needed. So if, let's say, the strains in the axial directions 1, 2 and 3, or x, y and z axes are represented by epsilon v1, epsilon v2 and epsilon v3. So this constant volume criteria or constant volume relationship requires that if one of them has positive, the other one should be negative, so that the overall volume of the bulk of the material, or the bulk deformation bulk of the material which is being deformed, that volume doesn't change, okay. And so that's how the first sort of premise would be when we are talking about plastic deformation. And the other one is that in metal working processes generally the compressive stress and strains are predominant, so we would be mostly concerned with the compressive stresses or strain. Otherwise, so unless we are otherwise trying to model a process like wire drawing, where there is a combination of both the compressive as well as axial stresses in tension which are happening combinatorially. So for conventional the systems, the strain is generally recorded as the change in length per unit origin length, and the true strain, as I earlier illustrated, is recorded as minus natural log of the initial height by the final height, or the initial dimension by the final dimension. So these are some useful tips for studying metal forming processes. The other issue about really investigating the flow stress region is the flow curve, and as I mentioned earlier, the flow curve is an accurate description for the stress strain behavior in the metal forming region, okay, the region where the metal forming really happens. So we are all concerned with what is the functional relationship between the flow stress along the curve indicated here, after the elastic limit has been exceeded. So basically it indicates the strength property that determines the forces and the power which is required to accomplish a particular forming operation. Whenever you are designing a forming process, you need to estimate what is going to be the power needed for formulating certain planned shape and size of the metal under the constant volume deformation criteria. So the flow stress in this case is defined as the instantaneous value of the stress required to continue the deformation of the material and keep the metal flowing, okay. So that is why we call it flow stress. So it goes into the flow region and the metal can be flowed into various shapes and sizes, okay, so which is the basic essence of all the forming processes. So the yield strength of the metal, if we really want to look at the yield strength as a function of the strain, it can be expressed by this relationship here, YF equal to k epsilon to the power of n. I think we had just detailed this relationship earlier. Only thing is this YF is the flow stress in the flow region, particularly in MPa megapascals, and epsilon is basically the strain. So if we were to look at the average flow stress, it can also be written down as 1 by epsilon integral of this yf d epsilon, where this epsilon is actually the maximum stress. So initially we can assume this to go between 0 strain, okay, all the way to epsilon is the maximum strain, we can assume it to go between 0 to the maximum strain, and that is how the average flow stress, which can be recorded as yf average, is represented. So this can also be then just substituting this value k epsilon to the power of n represented as k epsilon n by 1 plus n. Okay, so this is how the average flow stress is sort of determined by integrating the flow curve equation between 0 and final strain values, okay, defining the range of interest. So in this particular equation, one has to remember that this epsilon is actually the maximum strain value that happens during the whole deformation process. So that is how the average flow stress yf dash is recorded. Let us actually look at some numerical example problems for calculating all these average flow stresses, etc. Let us say the first problem is that the strength coefficient is about 550 megapascals. So that is how the K value is 550 megapascals, and we are looking at a strain hardening exponent n value of 0.22, okay, for a certain metal, and during forming operation the final true strain that the metal experiences is actually 0.85. So we are talking about the final true strain is also the maximum true strain, you can say, in a increasing curve as shown before in the flow region. Okay, so this is the maximum true strain, and this is shown as 0.85. So obviously the yf value, the flow stress at this particular strain can be recorded as k epsilon to the power of n. K is 550 megapascals times of 0.85 to the power of 0.22. That comes out to be about 531 megapascals. And if we looked at the average flow stress, again we use the same formulation, that is integrating the yield curve equation over the whole strain domain, substituting the maximum strain value, we get the average flow stress yf dash as k epsilon to the power of n by 1 plus n. So in this case we have 550 as k, epsilon is 0.85, n is 0.22 by 1.22. So this comes out to be equal to about 435 megapascals. So you can see that whereas the maximum yield stress comes out to be about 531 megapascals, if I wanted to average this over the whole force, over the whole stress strain curve area and divide that by the maximum strain, the final true strain, this comes out to be only 435 megapascals. So the average is lower in comparison to the flow stress at the maximum strain point, so which happens more or less in all the cases. So let us also look at this another problem example. So there is a metal which has a flow curve, the strength coefficient in this case is given as 850 megapascals. So the K is 850 MPa, and in this case the strain hardening coefficient N is recorded as 0.30. We have again a tensile specimen of the metal, and this has a gauge length of 100 mm and is stretched to a length of 157 mm. So we actually know the true strain value here. True strain, as you may recall, is also represented by the relationship minus ln initial gauge by the final gauge. Okay, so in this case it is minus ln initial gauge by final gauge, and this with this true strain and this exponent of the strain hardening and the strength coefficient values, we can determine the flow stress at the new length. So basically at this particular strain value, maximum strain value, the flow stress YF could be represented as 850 times of this value here, true strain, to the power of 0.30. So this value comes out to be, so this becomes equal to 0.45. And if we wanted to calculate the true stress value, or the yield in this yield region or the flow region, YF, so the YF becomes equal to the K value, which is 850 megapascals, times of the 0.45, the true strain epsilon to the power of the strain hardening coefficient, which is 0.30 in this case. N here, as you can see, is equal to 0.30. So this becomes equal to 669 megapascal. Similarly, if we wanted to find out the average flow stress, it's actually represented as K epsilon to the power of n by 1 plus n. We already know what is this K epsilon from the last to the power n, from the last step, 669 megapascal. So we just divide that by 1.30. Remember, this n is 0.30. So this happens to be 514 megapascal. A few more questions which I would like to do. In this particular example, the metal has a flow curve with the strength coefficient given by 35,000 pounds per inch square. So we'll have to convert this into megapascals, and the strain hardening exponent in this case is given to be 0.26. You have a metal with an initial gauge length of about 2.0 inches, and this is stretched to a final length of 3.3 inches. So obviously there has to be a true strain value associated with it, and we have to determine what is the flow stress at this new length, and also the average flow stress that the metal has been subjected to during the deformation. So let's first record all these values. The strength coefficient K for this curve happens to be 35,000 pounds per square inch. We already know the conversion, 1 pound per square inch can actually be written down as 0.00689 megapascals. So having said that, the K value can be recorded as 241.15 megapascal in this particular case. We already know that there is a initial gauge length H0 of 2.0 inches, which gets into a final gauge length H1 of 3.3 inches. So the true strain value in this particular case, epsilon, can be recorded as minus ln of the H0 by H1 as per formulation derived earlier. So minus ln 2 divided by 3.3, in this particular case it happens to be 0.50. So having said that, now the ultimate the yield strength, or let's say the flow stress YF, which is needed to be found at this new length, can be written down as K epsilon to the power of n. So 241.15 times of 0.50 to the power of n, which is in this case 0.26. It has been given as 0.26. So this happens to be about close to 201.38 megapascals. Similarly, if I were to find out what is the average flow stress, is represented by K epsilon to the power of n by 1 plus n. So in this case it happens to be 201.38 divided by 1.26. Remember, n is equal to 0.26. So this comes out to be 159.82 megapascals. Similarly, we have this other question here in which there is a tensile test conducted, and where there are two pairs of values of stress and strain which are recorded for the specimen metal after it has yielded. So now the metal has gone into the flow stress region, and it can actually obey the relationship, the flow stress equals to K epsilon to the power of n. So we have a pair of two stress and strain values. In one case 217 MPa, the YF is actually represented as K times of 0.35 to the power of n. Let's suppose that K is the strength coefficient in this particular case, and let's also suppose that n is the strain hardening exponent. These two have to be determined. So the other case or the other value or pair of values are corresponding to 259, and the true strain recorded is 0.68 to the power n. So these relationships are obeyed because both of them are in the flow region, and the stress strain characteristics follows the flow curve. So we can actually have a ratio between 1 and 2. So 217 by 259 comes out to be 0.35 by 0.68 to the power of n. If I take so this becomes 0.838 equals 0.514 to the power n. So taking natural log on both sides, we have ln 0.838 equals n times of ln 0.514, and in other words n becomes equal to 0.26. okay. So with this new n value, if I wanted to record by substituting back into one of these equations what is the k value, the k value comes out to be equal to 217 divided by 0.35 to the power of this new n value which has been recorded, and this comes out to be about 294 megapascals. So as you can observe here that the strain hardening coefficient happens to be about 0.26 and the strength coefficient happens to be 294 megapascals. So this is how you basically try to calculate the various parameters in the flow curve in the flow region, and it's very important property because all metal forming typically happens beyond the elastic limit, and whatever we are going to do in the following lectures about forming processes are really going to be concerned with this flow region of the particular curve. So I'm going to, in the interest of time, close this particular module, but in the next module we will look at some of the criteria which are used for arriving at a point where yield starts really. So these are known as the yield criteria, and we will derive some of them with energy principles and other first principles. There are two different criteria which are very commonly used. One is called the von Mises criteria, another is the Tresca criteria. So we will derive all that from first principles and then start applying to the metal forming processes, and we are going to do modeling of one or two processes in the way like rolling or maybe even some bending processes, and the whole goal here is to operate in the flow region and be able to identify when the flow region starts really, so that you could get the exact powers or exact forces which have to be applied for the metal to be able to yield and to be able to follow the flow behavior. So with this we will like to close this module. Thank you very much for being with me. Thank you.